I am Dinesh Lakawat from the IT department, section A, first semester. Now let us talk into the topic matrices and calculus. Now let us start our topic. Applying eigen decomposition in principal component analysis of a sensor data. Introduction to PCA and sensor data. Principal component analysis (PCA) is a statistical method used to reduce the dimensionality of sensor data sets. Sensor data often contains high dimensional information that can be challenging to analyze directly. PCA simplifies this data while retaining the most significant variance components, adding in interpretation and visualization. This is the introduction to PCA and sensor data. Now, let us talk some importance of eigen decomposition in PCA. Decomposition is a core mathematical step in PCA that helps identify principal components. It involves decomposition the convariance matrix into eigenvalues and eigenvectors. This process reveals the directions of maximum variance in the data. Understanding sensor data characteristics. Sensor data can be multidimensional, including variables like temperature, pressure, or acceleration. It often contains noise and correlated features that complain analysis. Proper pre-processing is essential for before applying PCA to sensor datasets. Data processing. Standardize or normalize sensor data to ensure each feature contributes equally. Handle missing or inconsistent data through implementation or flirting. Center the data by subtracting the mean of each feature to prepare for convariance calculations. Constructing the data matrix. Arrange sensor measurements into a data matrix where rows represent observations and columns represent features. Ensure data is properly scaled for accurate PCA results. This matrix serves as a foundation for a convariance matrix computation. Computing the convariance matrix. Calculate the convariance matrix to understand feature relationships. The convariance matrix is symmetric and captures pairwise features convariance. It provides the basic for eigen decomposition in PCA. These are the computing for convariance matrix. Eigen decomposition of convariance matrix. Decompose the convariance matrix into eigenvalues and eigenvectors using eigen decomposition. Eigenvalues indicate the amount of variance explained by each principal component. Eigenvectors define the direction of the principal components in feature space. Interpreting eigenvalues and eigenvectors. Larger eigenvalues are corresponded to more significant principal components. Eigenvectors are orthogonal, representing uncorrelated directions in data. Sorting eigenvalues in descending order helps identify the most important components. Selecting principal components. Choose the top eigenvectors based on their eigenvalues to form the principal component space. The number of components selected depends on the desired variance retention. This selection reduces data dimensionality while preserving essential information. Projecting data onto principal component. Multiply the original centered data by selected eigenvectors to obtain principal component sources. This transformation simplifies the dataset, highlighting key patterns. The scores can be used for visualization, classification, or further analysis. Visualizing sensor data in reduced space. Plot principal component scores to visualize data, cultures, or trends. PCA plots help identify anomalies or sensor faults. Visualization aids in understanding complex sensors datasets. Some benefits of eigen decomposition in PCA. Eigen decomposition provides an exact mathematical solution for PCA. It efficiently extracts the most significant features in high dimensional data. This approach enhances data interpretability and reduces computational complexity. Now, let us talk some applications of PCA in sensor data analysis. PCA is used for fault detection and condition monitoring in industrial sensors. It facilitates features extraction for machine learning models. PCA assists in sensor data compression and noise reductions. These are the some applications of PCA in sensor data analysis. Limitations of eigen decomposition in PCA. Eigen decomposition can be computationally intensive for very large data sets. It assumes linear relationships between features, which may not always hold. Proper processing and parameter selection are critical for meaningful results. Enhancements and alternatives to eigen decomposition. Techniques like singular value decomposition (SVD) can be used as alternatives. Kernel PCA extends PCA to capture nonlinear relationships. Incremental PCA allows for processing streaming sensor data efficiently. Practical implementation steps. Collect and pre-process sensor data, ensuring quality and normalization. Compute the covariance matrix and perform eigen decomposition. Select the principal components and project data for analysis or visualizations. Sensor data in manufacturing. Sensor data from machinery was reduced using PCA to identify operational patterns. Eigen decomposition revealed key vibration modes linked to machine health. The approach enabled predictive maintenance and reduced downtime. Best practices for applying PCA to sensor data. Always pre-process data to remove noise and normalize features. Carefully select the number of principal components based on explained variance. Validate PCA results with domain knowledge and additional analysis. Future directions in sensor data PCA. Combining PCA with machine learning enhances predictive analytics. Real-time PCA enables dynamic monitoring and fault detections. Integrating PCA with other techniques can improve robustness and insights. Now let us conclude our topic. Conclusion and summary. Eigen decomposition is a fundamental step in applying PCA to sensor data. It helps uncover underlying structures and reduces data complexity. Proper implementation of PCA enhances sensor data analysis and decision makings. Thank you for listening.